You are listening to The Vocal Technologist. Spoken tech for your ears.
Tools are getting better. Output is getting worse. Both are true.
It is the great paradox of our current tech cycle. We are writing code faster than ever before, and, well, we are breaking production faster than ever before.
Welcome to Vocal Technologist. Today we need to take a proper look at a massive collision happening right now in software development.
Yeah, we're going to pick it apart.
Yeah.
Because AI-assisted coding is fundamentally breaking traditional DevOps and, infrastructure guardrails.
And we really need to suss out how the industry is frantically trying to rebuild the foundation up to and including rewriting entire databases from scratch.
The stakes here are entirely structural. Like, we are actively moving from a world where human engineers fully comprehend the systems they build to a world where we are managing fleets of autonomous agents.
And code bases we barely recognize. I've got to be honest, my brain melts a bit thinking about the sheer scale of this.
Oh, absolutely.
Like, if you are listening to this on your commute right now, think about the last time you had to review a colleague's pull request. Now multiply that by 1,000.
Because we are dealing with just an overwhelming volume of AI-generated code.
And the wildest part is this stark data point. Most development teams actually rate AI-generated code quality as higher than human-authored code during the review process.
Which, looks fantastic on a performance dashboard, doesn't it? It feels like a massive win.
Right up until the pager goes off at 3 a.m. Because shipped AI code actually leads to 78% more incidents in production.
78%.
78%. I reckon that completely shatters the illusion that we are shipping better products. Like, if the code looks brilliant but breaks the servers, what are we actually doing?
What we are doing is participating in a systemic failure of quality assurance. The harsh reality we have to face is that traditional code review, the way we've done it for 20 years, is becoming obsolete.
Right.
It is pure theater at this point.
Code review is theater. That is a brutal way to put it.
But it's the only mathematically accurate way to put it, honestly. Think about the physical mechanics of a pull request. Historically, an engineer spends a day or two writing a feature.
Yeah.
And another engineer spends an hour reviewing the logic, the edge cases, the style. But now, an AI can generate 1,000 lines of syntactically perfect, highly plausible code in seconds.
So the sheer volume of pull requests just completely outpaces human reviewers.
Exactly. You simply cannot read, let alone critically comprehend, code at the speed a machine generates it.
So people are just rubber stamping it. They look at it, it looks clean, it passes the basic syntax checks, no glaring red squiggly lines in the editor, and they just hit merge.
They do.
Because the data backs that up. Over 60% of leaders admit their teams are shipping AI code without line-by-line manual verification. They're having a lend of themselves if they think that is safe.
And that is exactly why the industry is rapidly shifting quality assurance away from manual review. We're having to rely heavily on automated deployment pipelines.
Strict policy-based checks.
Yes. Manual code review still has a place, but strictly for mentorship, knowledge sharing, and high-level design feedback, it is no longer a reliable safeguard against bugs.
It is actually worse than just missing bugs, though, isn't it? There is this psychological downside to this whole AI-assisted dev process.
Yeah.
It changes how developers actually think about the problems they're supposed to be solving.
That is the critical engagement piece that gets ignored.
Yeah.
The faster implementation loop we get from AI fragments and engineers' attention, it actively weakens design discipline.
Right.
When you can generate a working prototype in 10 minutes, you are highly encouraged to ship your assumptions before you actually understand the user's needs.
So the work shifts away from deep problem solving and turns into this endless, fatiguing cycle of specification, monitoring, and repeatedly correcting unfamiliar code.
Exactly.
It is like bolting a Formula One engine onto a rusted-out farm tractor. The pipeline just isn't built to handle that kind of speed without parts flying off.
No, it isn't.
The tractor was designed to plow a field slowly and carefully, and now it is doing 200 miles an hour while the wheels literally rattle loose.
That is an incredibly apt visualization, and it highlights why we need to completely change how we measure success. For a long time, the industry was focused on token maxing.
Right, measuring developer experience, or DevX, by how widely AI was adopted or how many millions of tokens were being processed.
Yeah, like, look at how much our devs are talking to the AI. We must be heaps productive.
Exactly. But churning through tokens doesn't automatically create better outcomes.
We have to measure by delivery outcomes and system health. You have to measure the impact across the entire software lifecycle.
Hmm.
Are we seeing fewer bottlenecks, reduced rework?
Better business outcomes.
Because if you are generating 10 times the code but spending 20 times the hours fixing production outages, your developer experience hasn't improved. It is actively degrading.
Okay, so if humans are burning out trying to review the code and our attention spans are getting shredded, it feels like the natural and slightly terrifying next step is having AI agents just do the background work for us.
Right.
Cut the human out of the loop entirely.
It is the logical evolution. If the bottleneck is human review and human integration, you remove the human from the routine tasks.
And we are seeing this work incredibly well in specific bounded scenarios. The GitHub team used their agentic workflows to automate cross-repository documentation.
Right.
And this wasn't just some weekend toy experiment. They had AI agents producing 82 merged pull requests with a median turnaround time of under 45 hours.
Which is massive.
It massively reduced the manual reverse engineering that human devs usually have to slog through just to figure out how old code works.
And that is just documentation, which is relatively safe. The open source community is taking this much, much further. Look at systems like LobeHub.
Oh yeah, LobeHub.
It's an open source platform that lets you build and manage teams of AI agents operating 24/7.
Teams of agents. Like a completely virtual automated workforce sitting in your servers.
Yes. Automated hiring of specific subagents, scheduling collaborative workflows between multiple models, or look at OpenInspect.
Right.
It automates background refactoring and bug fixes across multiple repositories while your human team sleeps.
Right, hold up. I have to jump in here. Because if we have invisible agents sprinting around our repositories, reading our proprietary code, merging pull requests, and operating all night, who is actually watching the watchers?
Well, that is the million-dollar question.
How is this not incredibly dodgy from a security perspective? My gut says we are just opening the front door and hoping for the best.
It is a massive vulnerability if handled poorly, which it often is. You cannot secure an autonomous agent the way you secure a human. With early AI tools, security was mostly prompt-based.
You'd basically inject a hidden instruction telling the AI, please do not write malicious code or read files you shouldn't.
Which is literally like asking a burglar nicely not to nick the telly on his way through the living room. It's barely a suggestion.
Right. It is trivial to bypass. If a bad actor feeds the agent a clever prompt, the agent forgets the rules.
Exactly. And the infrastructure response to this is moving to the environment level. Take NVIDIA OpenShell, for example. It's an open source runtime that sandboxes AI agents with kernel-level policies.
Okay, for anyone who hasn't poked around in operating systems recently, break down what a kernel-level policy actually means in practice.
The kernel is the core brain of the operating system. It controls everything: hardware, memory, file access. Instead of asking the AI to behave nicely via a text prompt, OpenShell physically controls what the agent can do at that core OS level.
So it dictates exactly which files it can access.
Yes, what subprocesses it's allowed to spawn and heavily restricts its network traffic. It proves that agent security belongs in the hardened environment, not in a fragile text prompt.
Okay, that makes me feel slightly better. And then you have platforms like Fastly building edge network protection, specifically for these model context protocol servers, or MCP servers.
Right.
MCP is basically the new standard way for AI models to talk to external tools and databases, right? So Fastly is combining bot management and traffic optimization to protect that specific communication layer from AI-specific threats.
Because the nature of the threats is changing entirely. When you have autonomous agents acting on behalf of users, telling the difference between a legitimate human user, a helpful agent you hired, and a malicious bot trying to scrape your data becomes incredibly difficult.
Which leads to this brilliant detail from Cloudflare that genuinely shook me. They have a tool called Precursor. To tell bots and humans apart, they don't just look at IP addresses or cookie data anymore.
No, they dynamically inject JavaScript to continuously monitor client-side signals.
They are analyzing the physical biometric behavior of the session.
Right.
This is the part that blew my mind. They're measuring things like wrist pivot arcs.
Wrist pivot arcs.
The physical geometric arc your hand makes when you move a physical mouse across a desk. And cognitive delays, that slight, unpredictable pause a human makes when they are reading a paragraph or deciding what to click.
It is fascinating because automated bots, no matter how advanced the AI driving them, really struggle to replicate the inconsistent, messy rhythm of a human wrist and a human brain over time.
Algorithms naturally want to draw perfect, efficient curves. They want to be optimal.
But humans are chaotic. We
Mm.
have neuromuscular imperfections. We jitter, we overcorrect, we hesitate because we got distracted by a notification.
And Cloudflare is literally measuring those micro-stutters to verify our humanity. Think about that for a second. If you are keen on this kind of breakdown, hit subscribe on whatever app you are listening on right now.
It is an arms race, really.
Because here is the rub. Even if we lock down the security and we measure all the rest arcs in the world, the sheer weight of millions of agents hammering the network means the underlying infrastructure itself is crumbling.
Yeah, and that is driving this massive industry-wide push to rewrite core tech from the ground up. The foundational layers of the internet operating systems, databases, web servers were largely written in languages like C and C++ now. They are incredibly fast, and they've served us well, but they require the developer to manually manage memory.
Let's walk through that manual memory management because it is the root of so many evils. It is like being at a busy restaurant.
Right.
You ask the waiter for a table. That is allocating memory. You eat your meal.
Right.
But in this nick, if you leave without explicitly telling the majordomo that your table is free, that table sits empty forever. Nobody else can use it. That is a memory leak. And eventually the restaurant runs out of tables and the whole system crashes.
Exactly. Humans make mistakes. We forget to free the tables. That leads to memory leaks and catastrophic security vulnerabilities like buffer overflows.
Which is fine for a small script, maybe?
But when you're scaling up to handle massive fleets of AI agents, those human-made vulnerabilities become unacceptable.
Which is why we are seeing the sheer audacity of rewriting PostgreSQL. Postgres is a decades-old, battle-tested database written in C. It practically runs a massive chunk of the world's data.
Yeah.
And yet there are two separate massive projects right now, rewriting it from scratch in Rust, a language famous for its strict compile-time memory safety.
The scope of that engineering effort is just staggering. You have Torso Limbo, which is a new Postgres-compatible database written in Rust.
They're aiming to modernize the architecture for cloud-native deployments, right?
Yes, they're using asynchronous I/O, meaning the system doesn't sit idle waiting for slow disk drives to read data. It just moves on to the next task and comes back when the data is ready. They want to make distributed database features easier to evolve than they are in the legacy C codebase.
And then there is pcrest. This one is wild. It can actually boot directly from your existing Postgres data directories. It passed all 36,000 regression queries to reach full compatibility with Postgres 18.
And by shifting to a thread per connection model instead of a heavy process per connection model, they are claiming to be 50% faster on transaction workloads.
And roughly 300 times faster on analytical workloads.
300 times, just by changing the underlying language architecture and how it manages connections.
But here is where it gets really interesting and honestly a bit confusing. While Rust is clearly dominating this push for memory safety because of its famous borrow checker that acts like a strict librarian, ensuring you return every bit of memory, there is a counter trend starting to pull developers in a completely different direction.
Yes, towards a language called Zig. Rust provides incredible guarantees. If your code compiles in Rust, it's virtually impossible to have those restaurant table memory leaks.
But that safety comes with a very steep learning curve, highly complex abstractions, and painfully long compile times. The borrow checker can be notoriously difficult to satisfy. It fights you.
So developers are getting frustrated and looking at Zig.
But why Zig?
Zig makes a completely different set of trade-offs. It doesn't have the strict mathematical compile time safety of Rust. Instead, it offers a much simpler, stripped-down language for low-level systems programming.
Okay.
It still relies on manual memory management, but it forces it to be explicit. There's no hidden control flow, no hidden memory allocation behind the scenes. Everything is hyper-transparent to the developer reading the code.
Okay, so if C is like driving an old car where the brakes might randomly fail because you forgot to check the fluid, Rust is like flying a modern commercial jet.
Yeah.
It has got 1,000 pre-flight safety checks.
Yeah.
You physically cannot take off if a single sensor is misaligned. It is incredibly safe, but you need a 6-month training course just to start the engine.
Right.
Whereas Zig is like building a custom manual transmission sports car. You have direct access to the engine. It's incredibly fast. There's no computer taking over the steering, but you are absolutely trusted not to crash it into a wall.
That captures the dynamic perfectly. And as projects grow, the cognitive overhead of Rust's complexity starts to severely weigh on engineering teams. Zig's simplicity makes it easier to keep the entire system in your head.
Which is crucial for low-level programming where you need absolute control over the hardware.
Exactly.
Right. But here's the thing. We can debate Rust versus Zig all day. We can lock down our agents, but eventually the raw physics of infrastructure at scale catches up with you. The actual physical hardware limits.
Hardware in network topology will always dictate the ultimate upper limits of your system, regardless of how elegant your code is.
Netflix is the ultimate case study for this. They built a real-time service dependency mapping system to track their infrastructure.
And we are talking about processing millions of network flow records every single second across multiple global regions.
And when you operate at that scale, you hit problems that simply do not exist for 99% of companies. They ran into severe hot node issues where a handful of servers were suddenly handling 100 times more traffic than the others.
And the really wild part was what that traffic actually did to the system. It wasn't the business logic that failed, it was the garbage collection.
Right. They were originally using gRPC for this streaming architecture.
Right.
Let's break down gRPC quickly. It is basically a way for servers to talk to each other, but it is heavy, right?
It is powerful, but it requires constantly building and tearing down complex data structures for every single message. At Netflix's scale, that object churn was so intense that the garbage collection, the background process that cleans up used memory, was consuming more CPU power than the actual application logic.
The system was spending all its time and energy just trying to clean up its own mess.
Yeah.
It is like wrapping every single message in 3 layers of bubble wrap, putting it in a box, sending it, and then the receiver has to unbox it and throw the box away.
Yeah.
Eventually, your house is full of cardboard and you spend all day taking out the trash. So Netflix ripped it out. They switched from gRPC to server-sent events, or SSE, which is just a dead simple one-way pipe of data, no complex objects, no heavy wrappers. It massively reduced the overhead.
It is a perfect example of how complex abstractions completely break down under extreme physical load. It forces you to look really closely at the mechanical reality of how a CPU actually executes instructions.
Which leads us to one of the most counterintuitive performance paradoxes in modern systems engineering.
Oh, this one is brilliant, and it broke my brain a bit. Okay, so in computer science, there is this optimization concept called branchless programming.
To simplify it, normally when a CPU hits an if-else statement, a branch in the logic, it has to guess which path the code will take before it actually calculates it. If it guesses wrong, it has to throw away its work and start over.
That is called a branch misprediction, and it's a huge waste of time.
Right. Branchless programming uses clever math to eliminate those if-else branches entirely, so the CPU never has to guess. It just calculates a straight line.
Which sounds like it should always be faster, right? No guesswork, no mistakes, just pure mathematical speed. So developers use branchless binary search, assuming it's the ultimate optimization, but real-world benchmarks show it actually performs worse.
It does. Wait, hold up. That makes 0 sense. If you take the guesswork and the mistakes out of the equation, it has to be faster. How can waiting be faster?
Well, it performs significantly worse, specifically when memory latency dominates the execution time. It all comes down to a hardware trick called speculative execution and prefetching.
Okay.
Standard binary search uses those branches. The CPU uses those if-else branches to guess which memory locations it is going to need next, and it starts fetching that data from the slow RAM into the fast cache before it even knows for sure if it needs it.
Okay, so speculative execution is like a chef in a busy kitchen chopping vegetables before the orders even come in, just guessing that people will want salads because it's lunchtime.
Exactly. It overlaps the slow memory fetch with the fast CPU processing, but branchless implementations force the CPU to wait. Because there are no branches to guess from, the CPU has to fully calculate the exact next memory address before it can even ask the RAM for the data.
So branchless programming forces our chef to stand perfectly still, doing absolutely nothing until the ticket is printed and handed to them.
Precisely. It serializes the process. It eliminates the CPU mispredictions, the chef never chops the wrong vegetable, but it completely destroys memory-level parallelism. The ultra-fast CPU spends most of its time just sitting there, twiddling its thumbs, waiting for the slow memory to arrive.
It just proves that you can outsmart yourself if you ignore the physical reality of the hardware. But it isn't just about CPU cycles and memory latency. When we talk about the physics of infrastructure, we also have to talk about the human constraints. Because human time is a physical constraint of the system.
Often the most expensive and limited constraint.
Spot on. There was a logistics company recently that ran a massive production test comparing 3 reverse proxies, Nginx, Caddy, and Trafic. A reverse proxy is basically the bouncer at the club. It sits at the front door of your servers and directs all the incoming internet traffic to the right backend microservices.
Right.
They threw serious load at it, up to 61,000 requests per minute across a Kubernetes cluster.
And traditionally, Nginx is the gold standard here. It's notoriously fast and incredibly memory efficient.
It is. In fact, the data from the test showed that traffic actually used 11% more memory than the alternatives. If you were just looking at raw compute efficiency, you would pick Nginx every day of the week.
Yeah.
But they didn't. They chose Traefik.
Because of the operational overhead.
Exactly. Traefik has a deeply Kubernetes native approach, meaning it natively speaks the API language of the container system managing the servers. It doesn't need extra translation files.
Which is huge.
That architectural choice reduced their route configuration time from 23 minutes down to 4 minutes. It ended up saving the engineering team an estimated 6 hours of operator time every single month. They willingly, happily traded 11% more memory usage for 6 hours of human time.
Which is the exact synthesis of this entire conversation, really.
Yeah.
If you look at the macro trends we've discussed, whether it is a company replacing Nginx with Traefik to save human configuration time, or the industry moving away from manual code review toward automated deployment policies.
Or developers relying on Zig's explicit simplicity because Rust's deep complexity burns them out.
Exactly. The through line is incredibly clear.
We are desperately trying to buy back our own attention.
We have to. The real bottleneck in modern DevOps isn't compute power anymore. It is not network speed, and it is not memory latency. It is human cognitive load.
Yeah.
We are generating code at superhuman speeds with AI, and we are deploying autonomous agents to manage our infrastructure. Human brains simply cannot scale to review, comprehend, and manage all of it. The entire industry is frantically pivoting to tools that free up human attention.
The tech is getting infinitely more complex, but the winning tools are the ones that actually ask less of us. Which makes me wonder, when we finally succeed in abstracting away all this complexity and fleets of AI agents are running the entire show silently in the background, what happens to the next generation of junior engineers?
That is the real danger.
If the system never noticeably breaks in a way humans have to manually fix, how do they ever learn how the engine actually works?
It is a massive structural gap we are building for ourselves.
Something to chew on next time you are staring at an AI-generated pull request. Vocal Technologists, see you soon.
Spoken Tech for your ears.